put it suddenly half of the life, and we will try the incomparable number.
I don't remember it.
That is word for word. That is my favorite quote in the entire book. Number 16. I was number 14 over there. I was number 18. 17.
Mr. Townsend,
Sir.
I didn't get to come take the test today, so I was at the orthodontist still.
Okay.
Is there any way I could like go take a Spanish test and then come take the integer test tomorrow during advisory?
We went over the infinity stuff.
Yes,
where
if
it's
you
like
have time.
Over infinity.
Because I have barely any of a Spanish test left.
Okay. Yeah.
Something with exponent of infinity is infinity. Something with the exponent negative infinity is still 0.
Something.
Do you want me to take the quiz now, or why not?
I don't know which one I am.
I mean, you probably should because you've had time to get caught up, but it doesn't sound like you're caught up. So, if I was you, I'd watch the class video while they quiz.
We're turning
Okay.
84 as well.
Oh, crap, I can't listen to Gatsby. This is trouble. Trouble. I guess I'll just spark out, but still. I can't listen to it.
I felt like there was something, and then I was like,
No, but it's the end of the book. That's the thing. And also, I heard we gotta remember the last line of the book is extra credit.
Okay, if you did not turn in 83 and 84 in the Google Classroom, please make sure your name is on it and come turn it into the homework basket.
Okay.
Okay. This is a no calculator quiz, so you do need your desk cleared off, phones and smartwatches put up.
Are you Mr. Townsend?
No.
Good, I thought you were going to be late.
Late.
Later than normal.
Oh, because I had to see lunch today because we had like some sort of like hang
I
around.
feel like something
I'm
they
so
should have.
impressed. Stop. I don't care because everyone is like so coordinated. Since all of you are quirky, none of you are. So I'm like,
Why are you talking about quirky people?
Diego's the modern day philosopher.
yeah. So I don't care if people say that in band anymore because I know they're all like that.
So
They're all
quirky
drama
for talking about
queens.
that.
Thank
So
you.
funny.
Go ahead and get started, please.
I know.
Okay, unfortunately this quiz does not have point values, but each blank, each question you should expect to be 1 point. There's one question that gives you a table and a graph. The table is also worth a point and the graph is worth a point. So in the end that totals up to 26, I believe.
Oh, I should probably write my name. Can I borrow this? Sure. Somebody's Subaru Outback is really loud. Thank you, sir. Thank you.
May I take the quiz now, or do I not have enough time? Okay.
Because we need to move on when they're done.
Cool.
Why did I get a 5 out of 10 on this? Oh, just because I didn't do that one.
Mm-hmm. At least that one.
Oh, I did all the other stuff, so I did not get half off.
That's the way it's been all year.
Oh.
You
I
had
thought that was
time.
if it was late. Not bad.
Well, and if it's late. If it's incomplete, it's half. If it's late, incomplete, it's half.
Oh.
But you can still get half your points back. You just have to do it and turn it back in before the test. But I said it like 5 times that you needed to go back and do those.
Excuse me.
2. you. Okay, is anybody still working on the quiz? It's fine if you are. Okay, then let's move on. The two handouts you guys picked up today was 86 and 87. 86 is the one-sided quick one, and 87 is the longer one. So, what we did in section 1.9 with inverse functions, that stuff is important. That's why we took class time to do it. What we just did with section 3.1 and exponential functions is important. That's why we took class time to do it. But just for fair warning here, next up is 3.2, where we start getting into logarithms. But then 3.3 will also be about logarithms, and 3.4 will also be about logarithms. So starting right now, the next 3 sections will be all about logarithms, and some of this stuff builds upon other stuff. So this is one that you want to start off strong with and build a good foundation. Okay, so this first one is really about graphing a logarithm, and there's a few things that we've done in here that we need to kind of connect those pieces together, but really the only new thing is questions 1 through 3. After 1 through 3, and I show you a couple of examples, you know all of what you need to know to be able to graph these logarithmic functions. So you need to know this for graphing, and I think we put it on the quiz and the test, but you need to know the relationship between log base 3 of x and 3 to the x. They are both inverses of each other, which is why we did inverses in section 1.9 and then jumped all the way to chapter 3. Also, log base 8 of x and 8 to the x are inverses. So what do you think the inverse of 5 to the x would be?
Oh, sorry. Log 5.
Okay, log base 5 of x. And what would be the inverse of log base 2 of x? 2 to the power x. You guys see that relationship? How those match up? Okay, so if I wanted to graph something like this in question number 6, honestly what I would start with, even though it seems unrelated for just a second, I would actually start off with graphing 2 to the x. So that's an exponential function. We just talked about those. You can make a table, or hopefully you can just plot a few points real quick. 2 to the 0, 2 to the first, 2 squared, 2 to the third, exponential growth. So we've done that one recently. Since I just told you that these two are inverses of each other, and we have recently done inverses, inverse just means you're switching x and y. So the point 0, 1 becomes 1, 0, 1, 2 becomes 2, 1, 2, 4 becomes 4, 2, 3, 8 becomes 8, 3. You can switch over as many points as you need to, and then you know what log base 2 of x looks like, because it is the inverse of 2 to the x. Now, not that this is important right now, but remember, inverse functions have this line of symmetry at y equals x. So it's good to kind of notice that since they're on the graph there. Well, now that I know what log base 2 of x looks like, all I need to do is apply some transformation rules. So what happens when you add 3 directly to x? Okay, so take all of these points that we were sure about, scoot them over 3. And that is what h of x is. That's what it was asking you to graph for question 6. So it's not easy in the sense that you can just graph it right away. But if you look at that and you say, okay, well that would just be left 3 from what log base 2 of x looks like. And you can figure out what log base 2 of x looks like by graphing 2 to the x and switching all the points x and y because they're inverses. Then you can end up with what you are being asked to graph.
Now, kind of relevant here, but if you guys have more than one graph on your paper, you need to label these. Like I said, this guy was 2 to the x. I said this guy was log base 2 to the x, and I'm saying this guy is h of x. You shouldn't have more than one graph or more than one equation on a graph without identifying which one's which. Now, those 3 questions kind of push you in the right direction. Graphing 4 helps you understand how to graph 5, helps you understand how to graph 6. But realistically, what we want to aim for, maybe not right away, but after we practice this some more, gosh, next Monday, I don't see y'all again until Monday. It's a B week. Usually it's going to start off just like this. Graph that, which is way too much to start off with. So you need to realize that this is log base 3 of the x with some transformations, which is the inverse of 3 to the x. So we can quickly graph 3 to the x. And then his inverse, log base 3 to the x, would just be switching the x and y of all the points. I know this one's more tedious because it has more transformations, but it's still the same transformations that we've been using all year. If I plugged a number in for x, the first thing I would do is add 5 to it. So the first transformation you should do is shift it left 5. Just grab all of the points you were sure about and shift them all left 5. Now, maybe this doesn't bug you as much, but to me this is going to get to be too busy. I'm going to have too many things going on here. So I'm going to erase the stuff that I don't need anymore, just to kind of get it out of the way. I would suggest you just kind of graph lightly until you get to your last piece, but you can handle that the way you see fit. Okay, the next thing would be dealing with this negative, which is going to flip it over the x-axis. So any point on the x-axis is still on the x-axis. And it should look like it got flipped over. And then finally, I'm going to erase this one to get it out of my way. I don't need it anymore. It's really just a stepping stone to get to this. What's the -1 at the end going to do? Okay, so we've got a few points. Shift them down 1, reconnect. Make sure it looks like it just got shifted down 1, and then if you've got more than one graph on there, make sure you label which one is your final answer. So I of x would be this one. So again, same transformation rules. That's the last 3 steps. Graphing log base 3 to the x. You can use 3 to the x as a guide and just switch x and y, all of those points, because they're just inverses of each other. Now, of course, once you get the graph, we're going to ask you some characteristics, like the domain. Looks like he approaches -5 on the left and infinity on the right. X-intercept looks to be about -4.2. Once we learn a little bit more about logarithms, we won't estimate that. We will be able to give the exact value, but for right now, we're just going to estimate it. And then these problems have a vertical asymptote. Vertical lines have an equation of x equals, and so vertical asymptote is the line that it approaches but does not cross. So all of that is right there in front of you in the graph, but you got to be able to graph it correctly first. So we've talked about inverses, we've talked about transformations, we've talked about domain, x-intercept, and vertical asymptotes. But the main thing that's completely new on this one that you probably have not heard before, probably not even in Algebra 2, is to make that first little jump, you need to understand how those are connected. Okay, anything that jumps out at y'all about part 1 that you want to get clarification on before we move on to part 2? Christian, keep your hands to yourself.
I'm not touching them.
Okay. Still keep your hands to yourself.
Go ahead. We just play footsies.
Okay.
That
All right,
was a kid.
part 2. So on this one, we're going to talk about a few of the properties. We're going to talk about switching some forms, kind of highlight some of this that I know shows up on the ACT, but also start off with why logarithms are necessary, why we spend so much time talking about these. So if I ask you to solve this one on the left, 2 to what power gives you 4, you would tell me what?
2.
Because that's a nice even answer, that's pretty quick to do in our heads. Logarithm's not really needed. But what power of 2 gives us 5? Okay, good. It's in between 2 and 3. 2 would only give us 4, 3 would give us 8. But the point is, we can't give an exact answer to that right away without logarithms. So we're going to come back to that question right here in just a second. So one thing you should have learned in Algebra 2, and my other classes seem to remember this, but this is also big on the ACT, these next 2 sections, is switching from exponential form to logarithmic form. So these 4 are currently in exponential form. Logarithmic form is going to have the word log in it, but to add the word log out front without changing the question, you have to move a couple things around. So in this case, if you switch the 2 and the 9, it becomes logarithmic form. These are saying the same thing, just 2 different representations of it. If I switch the b and the c here, it's in logarithmic form. If I switch the 2 and the 16, it's in logarithmic form. And so what does this one look like in logarithmic form? Switch the 5 and the x. Log base 2 of 5 equals x.
I get that.
Now, this is what x equals. That's the exact answer to this question up there. While it may not be like super satisfactory because it's not a number that we're used to dealing with, that is the exact value of that answer. And before we're done with this handout, I'll show you how to change this to a decimal in case you wanted to see it as 3 or 4 decimals instead of just an exact value. So sometimes just switching, let's shoot, from exponential form to logarithmic form is enough to solve. If you do it and it gets you to x equals, then you have solved. And if you understand that direction, then you should be able to do the other direction without any more thought. If you want to take it out of logarithmic form, you want that to go away. So you basically have to undo the 2 things that you switch. The x and the 2 needs to switch place. The b and the c needs to switch place. The 8 and or the 11 and the x. And what would this one say? Again, these are saying the same things, just different representations. Now, you can't always check, by the way, like 8 to the x equals 11. That's true sometimes. It depends on what x is. But if you do get something that's true, like 2 squared is 4, that's a good sign. Now, again, these 2, you guys remember these from Algebra 2? No? Some yeses, some nos. Okay, these are the ones that I'm pretty sure show up on the ACT pretty often, and they're very easy to use, so good ones to review, good ones for you to see. All right, when it comes to using our calculator, your calculator has 2 logarithm buttons, a log, but notice if I hit this, it does not let me input the base, and there's one right below it, ln, which stands for natural log, and same thing, it does not let me put in a base. So you need to know what the bases are. These are supposed to be understood. So natural log just means log base e These are saying the same thing. So until you're more comfortable with natural logs, you should just always rewrite it as log base e. Same e that's in the compound interest formula, that same number. Again, just a different way to look at this, if we were trying to do something with it, is you could change this natural log to a log base e. That's all natural log means. If there's no base written, do y'all remember what that means? Good. It's an understood base 10. That's called the common log. So if it bugs you that you don't see the base, and there's no base written there, just squeeze in a 10, because it's an understood base 10. So when I hit the log button on my calculator, it assumes I want base 10. If I hit the natural log button on my calculator, it assumes I want base e. That's the two that it's been programmed to do.
Is there a thing in the math section
Where you can what?
put in whatever base you want?
Depends on your calculator, but I'm going to address that later too. Even though that's kind of nice to know, you don't want to use it as a crutch too much. So we're getting to that. Okay, we will ask you to evaluate some logarithms that are not without a calculator, without typing these in. These are all should be easy enough to do, but we need to make sure that we know how to read these. So the long way, which I'm only going to do once, but let's say I wanted to know the answer to this, so I'm just going to set it equal to x. So if I can figure out what x equals, then I have the answer to that question. Well, one of the few things we've talked about in our 20 minutes in logarithms is how to switch forms. This is currently in logarithmic form. What would it look like in exponential form? Okay, so you remove log, these two switch places. This is just a different representation. So 7 to what power gives you 7? So the answer to that question was 1. Now, I don't normally set it equal to x and switch the forms. I'm just showing you that you can do that if you need to. What I normally do, this is an understood base 10, is I just phrase it in my head this way. 10 to what power gives me 100? It's not multiplication. 2. 10 to what power gives me 10? 10 to what power gives me 1? Louder? 0. Anything to the 0 power is 1. I told you were going to hear that one a lot for a few weeks. 3 to what power gives you 27? Not 9. It's not multiplication. 3. Don't fall into the multiplication trap. What about this one? What is this? If this natural log bugs you, you can rewrite it as base e. What's the answer to that?
What?
1. This is saying e to what power gives you e? So it would be 1. E to what power gives you 1?
0.
0. Anything to the 0 power gives you 1. Basically the same as the one down there. And of all of these, this one's a little bit harder, so I would put a star by this one. What kind of exponent do we have to put on 2 to make it be 1/2? Very good, -1. A -1 exponent in the numerator is the same as a +1 exponent in the denominator. So 2 to the -1 is what gives you 1/2. So as long as you know how to read those, as long as they are nice whole numbers like that, there's no reason to get out a calculator. In fact, if you opened up your textbook, there's probably a table in there, and it probably calls half of these properties. Like it probably says, this is a property you need to memorize, this is a property you need to memorize. Probably all of these. But if you know how to read them, you don't have to memorize anything. You just have to know what it's asking you to do. And of course, be careful not to accidentally do multiplication instead of exponents. Okay, so how to evaluate logarithms without a calculator. So let's say with a calculator. Let's say I wanted to estimate this as a decimal. Like I was building something and I needed to like actually cut a piece of wood or something. So I don't really want the exact value. I want to know what it is as a decimal. Well, first off, we can estimate this reasonably. Christian, do you need something?
Sorry, I'm asking if he needs a calculator.
Okay, he's his own person, he can handle it. Okay, so what answer would be too small for this?
1.
Okay, how come?
3 to the power of 1 is 3.
Okay, and we need it to be 7, right? And what would be too big?
3 squared.
Because 3 squared would be 9 and we only want it to be 7. So do you see how you can tell without a calculator that your answer needs to be between 1 and 2? And the fact that 7 is closer to 9 than it is to 3 means the answer is probably closer to 2 than it is to 1. But sometimes we need to be more accurate than that. So there is something called the change of base formula. And this allows us to type this in our calculator, even though some calculators, when you hit the log button, it does not ask you what base you want. You hit the natural log button, it does not ask you what base you want. But I want a base 3 and a base 5. Now, there are some calculators, and I will show you guys, that will let you type in those, but you still need to know change of base for a few different reasons. One is, I think it shows up on the ACT sum. 2, I know they still ask about this in college algebra, so it's good for you to know what the formula is. And 3, there's a couple things in calculus that we prove with change of base, so you need to know what that is. But change of base just says that if you want to know what log base 3 of 7 is, you can do log of 7 over log of 3. Those are base 10. And or you could do natural log of 7 over natural log of 3. You just have to know which one goes on top and which one goes on bottom. But I will actually type it in both ways, partly to show you that they are the same. Both of them work out the same. I will also warn you, if it's on the ACT, it's going to be multiple choice, and in the past we've made it multiple choice. So you can't just learn one way. You need to know both of them. But that's about 1.771. So I had a feeling it was closer to 2 than it was to 1, but I couldn't get within 8 or 9 decimal accurate like my calculator can. So how could we type this one in the calculator to get a decimal out of it? Okay, or okay, both of those are this change of base formula. Now, again, in my opinion, I think change of base is kind of outdated because calculators are starting to move away from it. But again, until they stop asking about it in college algebra, until it stops showing up on the ACT, it is something we need to be familiar with. Okay, what would you expect the answer to this to be between?
5, 2, 3.
Not 5. We're not doing multiplications. 2 is going to be too big or too small? So our answer is going to be 2 point something. And since 27 is close to 25, that's why the answer was super close to 2. Notice same thing whether you do base 10 or base E, both of them work. So that's the way, no matter what calculator you have, as long as it can do logarithms and or natural logarithms, you can still get a decimal regardless of the base. You don't need a fancy new calculator. Okay, next up we want to look at a couple properties, and this first one's super important. This is the one that makes logarithms worth studying. I don't know why this is on here twice, but there is a property in logarithms that says if you have an exponent on something that you're taking the log of, that exponent can come down out front. And this is actually part of the daily meme for next class, although I guess you guys won't see it till next Monday. And while that might not seem important, it actually does something new for us algebraically that we couldn't do before. I would like to solve this. I would like to know what could I add to 2, make it the exponent of 4, and then come out to be 6. And you can spend all day guess and check here, and you're never going to get that, even though this is not like a big equation, not fancy numbers, no fractions, nothing like that. Because, now you don't have to know this first step right now, but just so you know, you can take the log of one side as long as you're willing to take the log of the other side. That keeps it balanced. The reason why we're going to do that in the future is because that makes this x plus 2 an exponent on something I'm taking the log of. So this is the only algebra trick we have that takes the variable we're trying to solve for out of the exponent and bring it down to where we're used to solving for it. You see why that's useful? Okay, and then, so this is kind of messy looking, but remember these two are just numbers, so you could distribute the natural log of 4. You could undo plus with minus, and then you could undo times with divide. So as I said, I could give you all day and you were never going to guess that. And to be able to pull that off, I really just used our normal equation solving the second half of the question, and the first two steps were kind of new. Knowing that property for step 2, the only algebraic property that's going to pull a variable out of the exponent is logarithms, which is how I knew to take the log of both sides so that I could pull that off. Now, just to also convince you, I'm going to type this in my calculator and store it. Partly because I want you to understand that this is actually the answer here. Okay, so as a decimal, here's what I'm saying the answer is. I told my calculator to think of this as x. And so this is supposed to be the solution to 4 to the power of, is it x plus 2? And that's supposed to equal what?
6.
So that is the exact value of x that makes that equation true. Yep.
Couldn't you have just done, because couldn't you just do natural log of 6 divided by natural log of 4 plus 2? Plug that in, it came out the exact same.
Natural log of 6 divided by natural log of 4.
Because they're both numbers, it's just written in.
Yeah, right here. See, when I distributed this, you divided that over, but
Yeah.
it ended up being the same.
Okay. So you don't have to write all that.
You just undid this multiplication, or you undid this multiplication before I undid this multiplication. I distributed first, but order of operations, you were consistent, so it was fine. It might make your answer look a tiny bit different, but it would be the same decimal. But my point is, just because, and this isn't going to happen too much in this section, but section 3.4 is all about solving equations. Just because your answer looks crazy and looks like an answer you've never gotten before, it might still be the solution to the problem. So we kind of have to get over that. Yes.
Will we have a calculator on the test?
Well, what have we needed a calculator for thus far?
Checking answers, more or less.
No, probably no calculator. I don't know about the test. Quiz is definitely no calculator. Okay, another property that we expect you to know, and unfortunately, I do show you an example of this now. I didn't used to do this, but really this is only really useful in calculus. We will still put 1 or 2 of these on our quiz and our test so that you're familiar with them. But there's a property, logarithm property, that says if you have a number to the power of log and the base is the same number of something, all of that's going to simplify to just a something. Let's write out a couple more examples. 3 to the log base 3 of 7 is just going to become 7. 72 to the log base 72 of 100 is just going to be 100. For your purposes in this course, you can get away with just pattern recognition. But we use this in calculus, which is why we expect you to see it before then, to work with something like this. And actually the first time they did this was just yesterday. But they're doing some calculus work and they get down to an equation like this, and they need to solve it for y equals, and it's currently natural log of y equals. while it might be tempting to think that you could just divide both sides by natural log, this is not natural log times y, it's natural log of y. So you can't undo it because it's not really multiplication. So you don't have to know this next step. It's good for you to see it at least once though. But there is a fancy algebra trick that's called exponentiating, where I'm going to make this all be the exponent of e. As long as I do it to the left and right side, that is okay. So now e to this is the left side of my equation and e to this is the right side of my equation. Well, what is e to the log base e of y? That's really the only way to dig that y out of that natural log like that. Without this property, we couldn't achieve that. So again, you don't have to worry about this. You can put an X, don't study, that's fine, but we will give you one or two of these on the quiz and test. So I've just given you some context to why it's important for you to have seen it before. All right, we did a few logarithms without a calculator, and we need to do a few more, but these are a little bit harder in that we need to use some exponent rules that go along with it. So 99 times out of 100 in math, if you have a negative exponent, you move it to the other side of a fraction to make it have a positive exponent. But you can go the other direction as well. An exponent of positive 5 in the denominator is the same as an exponent of negative 5 in the numerator. The reason why you should do this for this question is now because this is an exponent on something I'm taking the log of, so we can come out front. And what is the log of 10? Good. So understood base 10. 10 to what power gives you 10? This is 1. So your answer comes from negative 5 times 1. But if you don't think to rewrite that with exponent rules, it's kind of hard to get going. So let's rewrite this one as e to the negative 7th. Since negative 7 is an exponent on something I'm taking the log of, the negative 7 can come out front. And what's the natural log of e? It's 1. The base is e, so e to the first is e. So you're left with negative 7 times 1 to get that answer. It's just different. You're not used to making negative exponents. You're used to making positive exponents. If it has more than one sign, you need to make sure that you make both of them negative. So the x and the negative 1 need to switch signs. But then if it's an exponent on something you're taking the log of, you can bring it down out front. Times by the log of 10, but that's just 1. One more time, if you bring this up, make sure all of the exponent becomes negative, not just the first term. Then it's an exponent on something you're taking the log of, so it can come down out front, times the natural log of e, but the natural log of e is just 1. So you can have x's in your answer. We're not solving an equation here. Okay, we okay there? Anything that we've talked about that y'all want to get clarification on? If I'm going too quickly, you're skipping over what doesn't make sense, then it's defeating the purpose. So, okay, then got just a touch more here. So you need to have an idea of what the logarithmic graphs look like. So I think we may have done this one on your other handout, but log base 3 to the x is the inverse of 3 to the x. Log base 5 of the x is the inverse of 5 to the x. Log base e to the x would be the inverse of e to the x. Log base 10 of x would be the inverse of 10 to the x. So it goes back to when we did exponential functions, we graphed 2 to the x, we graphed 3 to the x. I told you 5 to the x would look basically the same, 10 to the x would look basically the same, e to the x looks basically the same. So their inverses basically look the same too. Not exactly, not point for point, but they all have an x-intercept of 1. They all have a domain of 0 to infinity. They all have a vertical asymptote at right here at x equals 0. So if I add 4 to x, what is that going to do to my graph? Left 4. So what's that going to do to my vertical asymptote? So that's going to put it at x equals. Right. So without transformations, if it's at x equals 0, you shift your whole graph left 4, your vertical asymptote is going left 4 also. So I don't even have to have that graph in front of me to know what the vertical asymptote would be. These two I'm a little more worried about, because I don't think you guys see this in Algebra 2 at all, and if you did, it was very little. So this would be log base 3 of x would have a vertical asymptote at x equals 0, but what does the negative right on top of the x do? Across the y-axis. So if it did have a vertical asymptote at x equals 0, and I flip my graph over the y-axis, do you still see how it's at x equals 0? Flipping over the y-axis doesn't change that, but adding 4 next to x, you're going to tell me that that's going to go left 4, correct? And I'm going to tell you that that's wrong. When you reflect over the y-axis like this, the rules for left and right translations are backwards. And the reason is, you should probably write it this way. The negative isn't really just going to the x, it's also going to a minus 4. So this is actually right 4. That is opposite of everything else that we do. If you reflect over the y-axis, the rules for left and right translations are opposite of what you're used to. So if it was at x equals 0 and I shift it left 4, now it's at x equals 4. Okay, where would the natural log of x, without any transformations, where would its vertical asymptote be? Without any transformations. 0. All of these are at 0. If I flip it over the y-axis, does that change where the vertical asymptote is?
No.
Still at x equals 0. And then adding 7 to x normally makes it go left 7, but because you're flipping over the y-axis, the rules are switched and it's actually going right 7. You guys okay with that? And you're more than welcome to graph that in your calculator if you want to be convinced that those rules switch. But the best thing I think you can do for yourself there is to maybe write it out like this, so you can see that the negative really is going to both of those, and that's why it's a plus 4, or just write it out in words. Okay, and then last part today, when we solve these equations, again, when we get to section 3.4, it'll be all about solving equations, and we'll work with harder ones, but for now we give you pretty basic ones. But you do need to know, when dealing with logarithms, you can create what's called extraneous solutions. Extraneous solutions is when your math is good, your logic's good, your arithmetic's fine, you don't make a mistake, but some of the answers you get just don't work. And what you have to start training yourself to think of is that it is not possible to take the log, regardless of the base, of a negative number or 0. You need to squeeze that in, or 0. And the reason why is, let's do like this. If I ask you to evaluate this, in your head you should be saying, well, 3 to what power gives me negative 1? Is there a power of 3 that gives you negative 1? That's why it doesn't work. If you think about the graph, 3 to the x, he never equals a negative number. It's not possible for that to happen. Also, he never can equal 0. He can approach 0, but those just don't make sense. They're not possible. So, how that's going to show up is if we ask you to solve this, notice this side has log base 3, this side has log base 3, so those two are already balanced. We just need to make sure that the insides are balanced. So set the insides equal to each other, take away an x from both sides, take away 5 from both sides, and this is a negative number. So what does that mean? not extraneous. And this is where you need to be careful. It's okay to have 0 as an answer. It's okay to have negative as an answer. You have to make sure that you're not taking the log of 0 or negative. So you actually have to plug it back in up here. See that if I plugged it in on the left, I would be doing this. And if I plugged it in on the right, I would be doing this. One thing is good for you to see that the left and right are equal. And 2 is good for you to see that you're taking the log of a positive number. That's the only thing that makes sense. That's not extraneous. You can have a negative answer. That's not the same thing as taking the log of a negative answer. So one more where you'll see that there is an extraneous, what it looks like when you have an extraneous part. So both of these already have log base 3 on both sides, so that's already balanced. We just need to make sure that the insides are balanced. How do we go about solving quadratics?
Put it all on one side.
Good. All on one side, set equal to 0, and then what? Factor or quadratic formula. You do all that work. You get 2 answers because it was a quadratic. One of these answers works and one of these answers doesn't. The only way for you to know that one of them doesn't work and to know which one to keep, if you include both of these, you're going to lose some points because both of these don't solve this. If I plugged in -3 into the original problem, you always have to plug into the original problem to check for extraneous solutions. I would get 9 minus 3, which would be 6, and -2 times -3, which would be 6. This is fine. I can take the log of a positive number. Left side equals right side. That's my answer. 1 does not work because if I had plugged it into the original problem, I would get log of -2 equals log base 3 of -2 equals log base 3 of -2. And while you might be happy that left side equals the right side, you cannot take the log of a negative number. That does not make sense. That's not possible. So this guy was extraneous and he should not be included in your final answer. So I will try to emphasize that and repeat that as often as possible because you do have to train yourself when you solve equations to plug it in and make sure it's not the log of 0 and not the log of a negative, because if that's the case then you can't include that as your answer. Okay, I don't really have a specific homework assignment for you guys between now and next Monday, but I would strongly suggest that you spend 5 to 10 minutes scanning through these 2 handouts. Again, we're going to be using some of this stuff, so the more familiar you are with it, the sooner, the smoother the rest of it will go. So most of this stuff is going to be used for the next several weeks. So please do yourself a favor and do that, please.